Just now we have introduced the concept of a group, but what is the relationship between group and this coloring problem? Let's look back. Just now, we are working on the quiz. We will find that the square is rotatable. Then if we paint the four top corners with symbols, respectively 1, 2, 3, 4. And this time, what will happen when it is rotating? We will realize, for example, if we performed a rotation, for example, 90 degrees clockwise, the original 1, 2, 3, 4 should become 4, 1, 2, 3. Then we will have such a thought, for this kind of rotation, can we use group to represent it? Actually, for this kind of group, it may use 1 to n to represent. We know it as a permutation group. Permutation group is very useful because for any limited group could be represented by it. Since there is a 1-to-1 correspondence between them, then what is permutation? Permutation is actually an arrangement. We will know that the number 1 to n, it can have many different types of arrangements. For example, 1, 2, 3 can be transformed into 3, 2, 1. And this time, correspondingly, we can write permutation into such a form. The top part is from 1 until n. The bottom part is what the corresponding 1 will be changed into, what 2 will be changed into. All these are 1-to-1 correspondence for all permutations. The number of n-order permutation is n factorial. Therefore, we will realize corresponding to all the permutations from a set, then we can assume they form group G. And corresponding to all of the permutations of the set, what are the corresponding operations should be? We have defined permutation multiplication. We already have two permutations, P1, 1 turns to 3, 2 to 1, 3 to 2, 4 transform into 4, and there are another P2, 1 turns to 4, 2 to 3, 3 to 2, 4 to 1. Now, let's take a look how to operate the permutation multiplication. Now, let's first look at the P1 times P2 because we first transformed from 1, 2, 3, 4 into 3, 1, 2, 4. Then the corresponding P2, it means to transform 1, 2, 3, 4 into 4, 3, 2, 1. To combine the corresponding P1, we tidy up P2. The corresponding 3 transformed into 2, 3 need to be transformed into 2, 1 need to be transformed into 4, 2 need to be transformed into 3, 4 need to be transformed into 1. And this time, we will realize, actually after permuting their arrangement, it has nothing to do with the order. We only need to ensure in P2, 1 turns to 4, 2 is swapped with 3, 3 is swapped with 2, 4 to 1. Then, it should be just fine. We will realize what was achieved through the multiplication. First, we need to do P1, 1 becomes 3. In step 2, 3 becomes 2, corresponding to P1 times P2. Their result has transformed 1 into 2. Corresponding to 2, it has changed into 1, and 1 is transformed into 4. Therefore, 2 needs to be transformed into 4. Because 2 and 4, 3 transform into 2, 2 transform into 3, 3 transform into 3, 4 transform into 4, 4 transform into 1. Then it becomes 4 transform into 1, P1 multiplied by P2. The result is 1, 2, 3, 4 is transformed into 2, 4, 3, 1. And this time we look for from another way round. For example, we operate P2 first, then P1. What will be the result? If we operate P2 first, 1, 2, 3, 4 will be transformed into 4, 3, 2, 1. And that time, we will tidy up P1 by following the sequence of 4, 3, 2, 1. 4 is transformed into 4, 3 transformed into 2, 2 transformed into 1, 1 transformed into 3. Therefore, at that time, we will select P2 again. 1 is transformed into 4, then 4 is transformed into 4. Because the answer is 1 transformed into 4. 2 is transformed into 3, 3 is transformed into 2, therefore 2 is transformed into 2. 3 is transformed into 2, 2 is transformed into 1, therefore 3 is transformed into 1. 4 is transformed into 1, 1 is transformed into 3, therefore 4 is transformed into 3. And this time we will realize the answer of P1 times P2. 1, 2, 3, 4 is transformed into 2, 4, 3, 1. But P2 times P1, the answer is 1, 2, 3, 4 is transformed into 4, 2, 1, 3. And this time we will have a conclusion of the realization of commutative law does not hold. Therefore, we just show an example which does not satisfy commutative law, and in this group is not the abelian group that we have mentioned. But this group satisfies associative law because the operation is multiplication. Therefore, it satisfies associative law. In the following section, let's prove that why the permutation set and its corresponding multiplication can form a group. We assume this permutation is defined on top of 1 to n. Then whether it satisfies the group's 4 rules. First, it is closure. 1, 2 until n. They are transformed into A1, A2 until AN. Any corresponding permutation from A1 transform into B1, into A2 transform into B2 until AN transformed into BN. According to this multiplication, we then know that the result will be from 1 transformed into B1, 2 is transformed into B2, until n is transformed into Bn. There is still a permutation, defined on the numbers of 1 to n. Therefore, it can satisfy the characteristic of closure. Corresponding to law of association, let's analyze on the characteristic of association. 1, 2 until n is transformed into A1, A2 until AN. The corresponding second permutation can be A1, A2 until AN are transformed into B1, B2 until Bn. Then these two will perform a combination. Then conduct a combination with a third permutation, B1, B2, B until Bn, C1, C2 until Cn, and this time the final result will therefore be 1 is transformed into C1, 2 is transformed into C2, n is transformed into Cn. What if we change the arrangement? We first transform A1 into B1, B1 is transformed to C1, and this time A1 is transformed into C1. Then conduct a combined multiplication with the first element. 1 is transformed into A1 and A1 is transformed into C1. The final result is still D is changed to C1. Therefore, we will realize regardless whether the first two are processed first or the later two are processed first, the answer that they got will be the same. Therefore, it satisfies association law about the identity element. An identity element should be the permutation. Their elements will remain unchanged. Then 1, 2, 3, 4, 5 until n. Correspondingly, we will transform into 1, 2, 3, 4 until n. That is a fixed permutation. We know it as an identity element. Use E to represent. Is there any inverse element? For permutation, 1 needs to be transformed into A1 and we need to transform it back. If it still manages to be transformed back to 1, then another permutation that A1 is transformed into 1 is sufficient. Therefore, 1, 2, 3 until n is corresponding to the inversion of A1, A2 until AN. It equals to the permutation by flipping them around. A1 is transformed into 1, A2 is transformed into 2, until AN is transformed into n. Therefore, and last we will realize corresponding to the set of multiple permutation with permutation multiplication, it can form a permutation group. Since permutation can form group, then we just raise an example. Let's take a look at the equilateral triangle. During its rotation, we can still consider its vertices. There are a total of 1, 2, 3 vertices. And then will it form a permutation group? We can first consider if this triangle keeps still, it will form a type of permutation. Corresponding to 1, 2, 3, they are still 1, 2, 3. Therefore, we can write it as P1. Next, it can be rotated. When it is rotating, there are many different angles. After the rotation of 120 degrees, it can still produce a new permutation result. For example, now we are looking at 1, 2, 3. If we have rotated 120 degrees, the shape of triangle is still the same, but the sequence number has changed. We will realize 1 has changed into 3. The initial 2 has become 1. Corresponding 3 has become 2. And this time, we will write out permutation P2, which is from 1, 2, 3 transform into 2, 3, 1. Of course, 120 degrees is a possible rotation degree. If it is rotated by minus 120 degrees, we still get a permutation. We use P3 to represent. Then accept the rotation from the middle. Actually, there is also an axis of symmetry. We can consider, are there any possibility to flip according to the axis of symmetry? For example, we fix the point 1, the respective point 2 and point 3 are exchanged. Then it will produce a new permutation, which is 1 is still 1, but 2 is transformed into 3, 3 is transformed into 2, corresponding to different points. Point 1 is fixed, we are corresponding to P4, and that time, if we fix point 2 and fix point 3, we will manage to get P5 and P6 correspondingly. And this time we will find out that corresponding to an equilateral triangle, it performed a rotation and flipping. It will form a permutation group. Of course, we will also realize if we want to have all the permutations, for example, under this example, corresponding to 3 elements, we have to perform all arrangement. It is actually 3 factorial, which is equal to 6 type. We will realize that what about the permutation of triangle if we consider of the rotation and flipping? It has already included all the factorial number into the calculation. And this time, it will form the largest permutation group. This is a permutation group we know as an n-order symmetry group. Usually we use Sn to represent corresponding to a triangle in total performing rotation and flipping what it can be formed, which is S3 is corresponding to such a symmetry group. There are a total of 6 different permutations, but not all the permutation groups need to enumerate all the arrangement. For example, under such a triangle rotation, I said flipping is not allowed, only rotation is allowed. It still form a group, and this group should be the subgroup of S3.